Right, good afternoon. Right, okay, so we're here to learn about parallel-ready Java code. I call this Managing Mutation in Imperative Language because the organizers wanted to think of a catchy title for what was going on in the Stream API. So I'd like to thank them for inviting me, and I'd like to thank you for coming to this talk. I'll just briefly introduce myself. That's how, whenever you have to give an introductory bio, I try and think of words to describe myself, and I come to the conclusion this actually means that you don't have a proper job. I'm a member of these programs, which are managed by Oracle to build the Java community. And if I'm known in the Java community at all, then it's by these two books. I'm a repeat offender. Mainly against myself, because writing books is a really horrible experience. I've written a book for each of or I was co-author of the first one. I've written a book for the second major release of Java, Java 5 and Java 8, having been the big releases. And my objection, my complaint against Sun and then against Oracle is that they left it 10 years in between these two releases, which was long enough for me to forget how awful the experience of writing a book is. So if they make the next major release a bit sooner than that, I'll know better. This is my hope. I also maintain the Lambda FAQ, which unfortunately is a bit neglected because of the effort of writing the book about lambdas. So what I'm going to do today is to talk about the Stream API. My intention is to try to do some work to reconstruct the ideas that the designers had in designing the API, which is a pretty kind of ludicrous thing for me to do because I wasn't actually present in the design and I didn't take part in it. But I did learn something about it through talking to them in writing the book Mastering Lambdas. And what I want to do is really to draw out the implications of their use of two very old ideas, pipes and filters and parallelism, and how these come together. If you're writing an API for a language which, like Java, is customarily mutates data. And that's what most programs in Java do. Mostly what we do is we create objects and we change their value. We change values in them, and then we store them again. This is typically what we do. And that actually means that we've got to do rather different things if we're going to support parallelism. And especially if we're going to do it with the idiom of pipes and filters than has been done before. And so there's some kind of novel aspects of this which I want to try to draw out. And then I want to talk about what it means to be what I mean by parallel ready and what it means for your code to be parallel ready. So to get some idea of how I should pitch the talk, could I see how many people are currently either programming in Java 8 or feel fairly familiar with the Stream API? Okay, so that's actually a minority of the audience, and I'm afraid I'm going to ask the people who do know about it to be a bit patient, because I'm going to go slightly slower over that. I'm afraid that for people who don't know the Stream API, then I will be going too fast for you, because we're in this uncomfortable situation now, or it's uncomfortable for me, where Java 8 is becoming adopted, and I never really know when I'm talking about it just how much I can depend on people knowing about it. And the second question I want to ask is, how many people came to Paul Butcher's talk in the previous session? Okay, so actually, you know all about this stuff already. You don't really need me to tell you about it. Some of what I'm going to say here overlaps, and some of it, I think, builds on that. I mean, one thing that Paul said was that it's a big jump to go from programming in an imperative language to programming in a functional language. And actually, one of the major objectives of the introduction of lambdas and of the Stream API in Java 8 was to make that jump very much easier. So although the word functional, it was kind of taboo for a really long time in the discussions about Java 8, actually the idea is to start to infuse some functional flavor into Java programming, and we'll see how that works. Okay, so first of all then, I'm going to talk about pipes and filters very briefly. This I really don't need to go into in a lot of detail because everyone knows about these in general. The idea of these derived from the original design of Unix, where they had the notion that joining together very small programs was a way of building large ones in a highly modular and easily recomposed way. So here we've got, in the top example, we've got a process here which reads the process table, searches it for a string, cuts out some characters from that, and then gives you the first 10 lines. And that rather complicated functionality is provided by these 4 different little processes which join together and can be joined together in a huge variety of ways to give lots of different, very complex programs, but very easily. The same idea has been taken over into enterprise integration patterns, and you can see the same kind of thing here, where we have incoming messages and they're decrypted and then they're authenticated, and then they're deduplicated. And the basic idea of working on this on a pipe, and filter here, of course, is the generic name for the individual processes in the pipeline, has turned out to be really fertile. So the advantages of this pattern, as applied, showing it in the Unix version, but thinking about it really in the Java version here, is we don't have intermediate variables. We aren't forced to pollute our namespace with a lot of intermediate variables. And going along with that, quite a lot of the time, we don't have to have a lot of intermediate storage. So typically for Java programming, if you had a bulk processing of collections, you would pull your values from a collection, you iterate over the collection, and then dump them in a new one. And then you do the same thing again with the new one and so on. So you'd have this intermediate storage, which led to problems with garbage collection and so on, and pollution of the program, and your program actually becomes really quite difficult to read. And I'm going to claim, though in passing here really, that the Stream API really makes, a lot of the time makes programs much clearer and more maintainable. Lazy evaluation is a possibility here. So instead of each individual operation being executed on all of the values in the collection, instead of that, all of the operations are executed on each value in turn. That means that if you're looking for a particular value or you're looking for a particular result, you're likely to be able to stop when you find it instead of having to go through all of the early stages for all of the different values. And of course, flexible tool building is really the key thing, because this philosophy allows us to build quite large and complicated tools, as I've already mentioned, from pretty small, and very specific individual tools. So Doug McElroy, who was the inventor of the Unix pipe, said it should do 3 things. We should write programs that do one thing well. We should write programs that work together. And he added that, for a third one, he added that we should write programs to handle text streams. Well, 2 out of 3 isn't bad. It turns out that it's not really, I mean, from our point of view, writing programs that only handle text streams doesn't really make an awful lot of sense, because we're writing an object-oriented language. But the principles, the first 2 principles there, work pretty well for us. So I'm going to have some examples here. The examples use a tiny domain, which you won't find it too hard to grasp. But we have a person object with 3 fields, and you can assume accessors and mutators on this, setters and getters, for the 3 fields. So they live in a city, and they have a name, and they have an age. And here's an example. We're constructing an example person here. This is Amy. She lives in Athens, and she's 21 years old. And we're going to assume that we've got a list of person, which we call people, which has got John and Amy and Bill in it. So some examples of the kinds of things that we can do with the Stream API are, and these are really almost the only examples of code that you're going to see in this talk. We're not going to have a lot of code, but just to give you a sense of the expressiveness of it, and the expressiveness and the conciseness of it, here's a way of computing whether or not everybody is an adult. I managed to alter this slide correctly. Sometimes I've given talks like this in Europe, and sometimes in America I have to go through and change the 21 to 18 and then back to 21 again. It's 21 today. So being an adult is this. So what we're doing is we're taking the list of people, the list of person, the people, and we're converting this, well, we're calling the stream method on it. Well, I'll talk more about this method in a moment, but basically what it does is it feeds the elements of this collection into a stream, and I will talk about what a stream is. And then each element in the stream is transformed by this method here. This is called an intermediate operation, which maps each element to an int, and the function that it uses to do that is the getAge function of person. Well, getAge is an accessor, obviously. This syntax here is called is a method reference which came in with lambdas, and you can read this as a more concise version of a lambda. So now instead of having a stream of person, we have a stream of ints. And now what we're going to do is we're going to feed them into this terminal operation, allMatch, which takes a predicate, a truth-valued function, this one in this case, for each value appearing in the stream A, it computes whether or not A is greater than or equal to 21. And if it's true, then that is a match. allMatch requires for this result to be true, for all adults to be true, that allMatch should be true. That predicate should be true for every element coming down the stream. So that's one example that's one of the two examples I'm going to show you. Here's the second one. In this case, what we're going to do is we're going to print the names of the inhabited cities. So we're taking the list of person here. We're streaming them. In this case, we're going to map them. Each person is going to be mapped to the city that they live in. And now we're going to execute the for each operation on a stream, which takes a method that returns no result, like system out print line, and it's going to and for each element coming down the stream here, it's going to print it out. So you maybe get a feel from this. I mean, people who know streams already will be drumming their fingers, and people who don't know streams already will be looking at this saying, "There's a lot of new syntax there." But I hope that you get the idea that this is actually really quite concise and expressive. It's clearly different in its style from the collection processing that we've been doing until now, but it's going to catch on. So from Java 8 onwards, this is what collection processing is going to look like. What are these streams? Well, they're sequences of values. They're rather hard for Java programmers to grasp the first time around. If you're used to Unix streams, then you can actually use these as a way of thinking about what's going on. They're not a collection because they don't hold values. They're something like an iterator in the sense that they yield elements for processing, but they never actually contain the elements themselves. They're not associated with any particular storage. So Brian Getz, the architect of the Stream API, likes to describe streams as being values in motion. So it's only while they're in motion that they're in there. There are many sources of streams, but the most important ones are collections. But we also have arrays, there are generators, the file API can produce streams, and so on. They can be parallel, which is going to be really important to us in this talk. They can be infinite, which I'm not going to discuss at all. And they have primitive specializations. So I'll be talking both about streams of reference values, which were like the stream of person that we had. And we also saw that at one point we mapped person to int, and then we had a stream of int, and that would be an int stream. And there are these three primitive specializations: int stream, long stream, and double stream. Well, now I'm going to talk a little bit about the different parts of a stream. So a stream has got sources, it's got transformation operations, which we call intermediate operations, and it's got sinks. I'm going to talk about the sources of streams very briefly. I'm then going to talk about the transformation operations, the intermediate ones. But when I need to talk about sinks, that is to say where streams end, I'll have to go off on a diversion there, because at that point the combination of streams of the pipes and filters idea with parallelism means that we actually have to think about what would the sink for a parallel stream look like. So stream sources, first of all, this is pretty simple, are for sequential streams. Basically, you can think of them like iterators. So for sequential streams, not for parallel streams, I'll come back to that, but for sequential streams, all that's required is something that can feed elements into a stream one at a time, essentially. So although all stream sources are implementations of this class java.util splitterator, interface, java.util splitterator, that the only part of this that's used for sequential streams is the iterator part of the splitterator. So this is a rather cute combination. It's something that can both split data sets and also iterate over them. I'll talk more about that tomorrow. If you're really a sucker for punishment, I have another talk tomorrow, and I'll be talking much more about splitterators there. But I'll show you a little bit about how splitterators work today. So the splitting part of splitterators is not important for sequential streams, but one thing to make clear right at the start, and it's very useful to understanding how the Stream API works, is that everything works the same way for sequential as for parallel streams. It doesn't mean you have to always execute your streams in parallel. In fact, tomorrow I'll tell you that nearly all of the time you don't want to do that. But nonetheless, all of the entire API, and also all of your code that uses the API, should be written as though it is going to be executed in parallel. And I'll explain the reason for that in a little while. So normally what you'll be using as the source of streams is the methods in the platform classes. I counted them up, and there's more than 40 of them. There's 44, I think, something like that in Java 8, including the most important one, collection.stream. And you've already seen me use that. So internally, of course, that uses a splitterator. And the intermediate operation, so that's the sources of sequential streams. Now the intermediate operations, the stream transforming things, these are things like, these are them actually. They're not like them, these are them. That you can filter stream elements, you can map them to other kinds of things, you can do one-to-many mapping, which I'll show you in a moment, and debugging, which I'll also show you. There's sorting and there's deduplicating, and there are these truncating operations, which I won't talk about more, but they'll allow you to either skip elements from the beginning or limit elements, that's to say discard them at the end. Here's a picture of what the filter operation looks like. Really, it's kind of, I don't want to insult your intelligence by showing you it, but I'm going to anyway. We're imagining here that we've got a filter operation here that in this case, we're filtering this string over a lambda here, which takes each element and compares and looks to see whether or not its length is less than 4. In this case, the first one that we got was Jim. It was a string Jim. That one passes, and so that element continues down the stream. The next one to come through is Bill, and he's got 4 characters in his name, so he doesn't pass the test. He doesn't continue down the stream. The third one is Amy. She passes, and she continues down the stream. So that's filter, and it couldn't be much simpler. Something similar applies with map. So we've got here where the map function here takes a person and transforms them to the city that they live in. So the input to this. To the map method here is a stream of person, and the output is a stream of city. You notice in the previous one it was a stream of string, both input and output. So Bill it lives in London, and the map operation transforms into London. London goes on down the stream. Let's skip the rest of this animation because it's kind of very simple. Peak is like the Unix T operation. It's essentially there for diagnostics. So this actually raises quite an important point. An element comes in from the left, from the input here, and the peak operation simply forks the stream in a very trivial way. So the element will continue on down the stream unhindered, and it will also be fed to a consumer, which is something like system out print line, but essentially it's any function which will take a value and return nothing. It may do something with it by side effect, but it will return nothing. System out print line is like that. So an important aspect of writing code that's parallel ready, a restriction on how you can use streams is you'd better not do anything with the value you're given here that affects the behavior of any other values in the stream. So for example, don't try and accumulate values here. Don't try and add them up by using a peak operation that accumulates them. That's going to break the rules for what you're allowed to do for your code to work correctly with the Stream API. The last intermediate operation I want to look at is flatMap, because this is sometimes a challenge to people who aren't used to the Stream API. The idea of flatMap is that each element of the stream is going to be turned itself into an entire stream, and those elements of each one of those component streams will be fed back into the output stream. So here's an example where the string Amy consists of these 3 characters, A, M, and Y, and that string is going to be is going to be fed into the cars method on string, which produces a stream of characters. Okay, so these now go down. You notice a small runway here. They go down that, and they then get amalgamated into the output stream, one after another. And the reason it's called flatMap is because it flattens those each one of these streams, which is generated for each element of the input stream. It flattens the output from those into one single stream. Okay, so that is all I'm going to talk about with the intermediate operations. I think you've probably got an idea of what's going on there. I want now to talk about sinks for sequential streams. But I can't talk about them for very long, because remember that the rule is that everything that works for sequential streams must also work for parallel streams. So some of these sinks are pretty straightforward. Find first finds the first element that satisfies a predicate. Find any finds any. It's explicitly non-deterministic. It finds any element that satisfies a predicate. We've seen all match already, and any match is similar to that. But obviously, it only requires one element to satisfy the predicate. You've seen for each, and for each ordered. For each is actually also explicitly non-deterministic, which comes as a surprise to many people. In practice, it will often reflect the order of the element in which elements are fed into the stream, but there's no guarantee that it will do so. The documentation says that it won't necessarily do so. For each ordered actually imposes that requirement that they will be in the order in which they come into the stream. Now we come to the big question about how are we going to aggregate the results of a stream. So remembering that we have to be able to work with any operation we use for aggregating the results of a stream as a terminal operation must work equally well for parallel as for sequential streams. So I'm going to get into a slight diversion here, but not a long one. Many of the ideas of the Stream API were inspired by the ideas of Guy Steele. There's one rather famous talk that he gave called "How to Think About Parallelism." How to think about parallelism, not. And the slogan that he had was the best way to write parallel applications is not to have to think about parallelism. And his idea was that that really we should be thinking about parallelism as the last stage in as the latest stage, I should say, not necessarily the last one, in a long procession of automations that have been done that have allowed programmers to lift the level of abstraction at which they think. And so he went through these, and I'm short of time, so I won't go through them in a lot of detail. But assemblers allow you to stop thinking about, force you to stop thinking about the absolute address of your code. You can't alter your code. There's people used to edit machine code within the program at runtime. You can't do that if you have an assembler. But you get something back in exchange. Now no longer do you have to remember machine codes. You can think about symbolic instructions. Linkers allow you to forget about the absolute address of, or they force you to forget about the absolute address of data. You only have the relative address of data now. But the result of that is it stops you from doing certain things, but it gives you a great deal of convenience, because now you can start to compose your programs from different. You can compile modules of your program separately, which is a huge advantage. And so on. Register allocation, you have to let go of your knowledge about registers, but the compiler does a lot for you. And so on and so on. Heap management, virtual memory, and the last one is parallelization. So he's thinking about parallelization as one of these automations. What is it that we have to give up in order to get automatic parallelization? And Guy puts this in terms of retooling. So a lot of the techniques that we've used in the past aren't going to work anymore. We can't, for example, get by reducing execution time by minimizing operation count. This is what we always used to imagine would make our programs faster. But if in fact what this means is that different threads are now going to have by reusing previously computed results, are going to have a communication overhead, it may be faster in the end, I mean overall, for the different threads each to compute the results separately and not to communicate. So you maybe have to waste operations. Same kind of thing about space. It may be that in the past we minimized space usage by sharing data, but from now on it may well be that the overhead of communicating between threads means that actually what we should do is just replicate the data in different places and so on. But the big one is that we're going to have to give up the idea. This one is much harder for us to accept. We're going to have to give up the idea of linear decomposition. So in the past, what we've done is the computation typically has processed one thing at a time to accumulate results. And now we're going to have to say, a lot of the time, we've got to take a step backwards and see that that's not necessary or even a good idea. And the example that I thought of that seems to have taken with people, they quite like this, is if you went to supposing you asked your friend to post some letters for you. You've got a big pile of mail, and there's a mailbox here, and you say, "Would you take these letters to the mailbox?" And your friend says, "Yes, okay." And you say to them, "But there's something important I need you to do, and that is put them into the mailbox in alphabetical order of addressee." And your friend would say, "Wait a minute, this is a bit micromanagement. This is you're being a bit over-controlling here." And rightly so. But actually, quite a lot of the time, when we write iterative programs, that's what effectively we're doing. We're imposing, because we don't know any other way of doing bulk processing than iterating in a defined order over a collection. We've come to think that iterating in a defined order over a collection is an essential part of the operation. And we need to kind of let go of that sometimes. We need to be prepared to say, we're willing to have things done in any order, or order is going to be a lot less important to us. And that gives wiggle room, as Guy puts it, to the implementation to allow it to optimize and to introduce automatic parallelization in this case. So, no more accumulators. And I just think that's amazing. But seriously, we're not going to have any more accumulators. Can we really do this? And some people think, well, we really can't. And this is one big change that we have to make to our thinking. We're going to have to give up using asymmetric operations. That means add a value to an accumulator. They're different. We're looking more for symmetric operations. I don't mean symmetric in the algebraic sense. I'll explain that a bit in a moment. And this is going to have a major impact on terminal operations because almost all of those are accumulations of some kind. So here's a really simple example of the way that we would normally do a very simple program. So in this case, all I've done is declared an array of ints, and now I just want to add them up. And this is the execution tree of the program that I've got here, and I'm just adding them up in the way that you would expect to add up the elements of an array. And of course, you will see that if you were distributing this work over multiple threads, you'd have to protect that variable with a lock, and the lock would get very hot, or else it would get very hot. The threads are going to want to have concurrent access to it, and I know everyone's been to Paul's talk, so I don't need to labour this point. So what do we do instead the standard response in functional programming is to introduce something called a reduce operation. And the reduce operation, I'm going to choose this overload. There's two of them in the Stream API. It takes an int binary operator. That means an operator on two ints, and that produces a result which is a third int. So the reduce operator, in this case, the obvious operator we want is addition. Allows us instead to write this. So we've got reduce over a. This takes an a and a b and returns a plus b. In other words, it's the addition operator. In the Stream API, you can do this more easily. You don't actually have to write this if you really want to add up but I'm doing this for demonstration purposes. So here's one possible execution tree using this, but here's another one. Right? So this will work equally well, and this is what I mean by a symmetric operation. Here, what we're doing is we're adding the result of applying the addition operation to these two elements. All right? So you can see here that working in this way allows us to see how we can split up a set of data, speaking broadly, a set of data like this, between different threads. And this is indeed the idea of using reduction. Reduction isn't going to be enough for us, as we'll see, but it's a start. An important constraint on the binary operator that we use here is that it's got to be associative, and that means that grouping mustn't matter. That means that A plus B plus C has got to be equal to A plus B plus C, because because either this or the previous execution tree are equally possible, and you don't know when you write your program which one's going to be executed. So they've got to give the same answer in whatever order, however the data set is broken up for this to happen. So now you can see that reduction primitives this is going to work quite well. I've got there's a blue thread and a green thread here, and they can each work independently on their own set of data, and they can be combined at the end. I chose the one with an identity. The identity is the element that gives you a starting point for this operation, and the binary operator here, which actually in this case is the same one as is going to be used for combining. So we've got an addition. We've got one where an element is added, and we've got one where two results are combined. So that works perfectly well for primitives, and it works also for immutable objects. But here's where the innovation came, here's where the difficulty came for the designers of the Stream API, because it doesn't work for mutable objects. I mean, it looks like it might do. We would need to have 3 functions instead of 2, because we're going to have an identity here, then we're going to have an accumulator. Imagine, for example, this is an array list that we're working with here. The accumulator here would be the add operation. You call add on your list to add a single element to it. So I start off with an empty list, and I add an element to it. I add another element to it. I add another element to it. The same thing's gone on here. And finally, I combine them with what would be the method that combines 2 lists. Add all, absolutely. So that looks like that would work perfectly well, but it doesn't work at all. All right? So can anybody see why it's not going to work? Why does reduction not work with mutable objects? Okay, you're in good company if you don't see this, because it took the designers of the Stream API a long time to do that. Reduction is given a lot more prominence in the Stream API than it should be, because it took a while for it to dawn on them this wasn't the right thing to do. You have to generalize reduction, something that people working in functional languages didn't have to do because they only had immutable objects. But if you have a mutable one, this won't work because the reduction operation expects that this identity will be the same for each thread. And so it's going to start off on the assumption, if you try to apply reduce to a list accumulation, for example, you will get the wrong answer because you'll get the wrong answer if you run it in parallel, because each thread will take the same initial list object and use that as the basis for its computation. And somebody else might already have been there and already have put something in it. So you get duplication of elements. So this is not parallel ready. And instead they had to invent something different, which is called collectors. The verb that describes it is collection, which is kind of confusing because we've already got collection. And instead, this replaces the identity method, the identity value, with a supplier, which is a function which takes nothing and produces an empty container. And each thread applies that, and of course, each one therefore gets a fresh empty container. So that's So the collector API is really the big deal in the Stream API. This is really where most of the complexity goes, most of the functionality, and you get a lot back from it once you've learned about it. And the predefined collectors they're created from factory methods in the collectors class, and these predefined collectors cover a huge range of your needs. And really, I could sort of stop the talk at this point because I could say, well, look, 99.9% of what you need is going to be covered by these collectors. I'm going to talk about them a little bit, but I'm also going to talk about what do you do when they aren't good enough for you. But the point I really want to ram home is they are good enough for you nearly all of the time. It's a really well-designed API, and the objects that it creates are very composable. So the nice thing about it is if one of them doesn't, not exactly like pipes and filters, but something like that. If you need a collector that isn't satisfied by what is provided in the collector's API, what you can usually create a new one by combining two together. So these predefined collectors fall into three categories. There's the first line is about, well, I've divided them into three categories. That was how I found it convenient to think about them. The framework can provide the supplier, as in the first one. So to list, to set, to map. Currently gives you an array list or a hash set or a hash map, and joining will concatenate strings together. You can, if you want to provide your own supplier. So in other words, supposing you want to accumulate to a tree set or something like, or a linked hash map. You can use the collectors from the second line, and for the third line. These produce what I call classification maps. So let's just take a quick look at the animations for a couple of simple collectors to give you a sense of what's going on. Here's what I'm doing in this case is simply something that you might think was really a bit trivial. I'm taking the list of person, I'm streaming them into the I'm creating a stream. Here it is, and I'm going to collect them into this toSet. Collectors. It's the collector that you get back from calling the factory method toSet on collectors. So my animation looks like this. Here comes Bill. The collector internally creates a set, and it puts Bill into that set, and John, and Amy. And when the stream is exhausted, when this stream here is exhausted, now then at that point the collector can say, right. I'll output that set. So you think that's a bit trivial. Let's look at one that's slightly less trivial. Here's one that will create a mapping from this ominous-looking signature here is actually describes something fairly simple. We're taking a stream and we're going to collect it into a collector which has a function which produces the key for a key map for a key value pair and the corresponding value. So let's have a look at how that works with our example here. Bill comes in. Bill lives in London. So person.getCity. That's the keyMapper has worked there, and now the valueMapper is going to work there. So it's going to get Bill's name, and now a new key value pair has been created, London to Bill. The same thing for Amy and Athens, of course. That went much too fast there. That was not at all what I meant to do. Have I hit the right point? Looks good. Okay, so I don't know why that happened. Okay, so Bill, all right, so we've got, so here's now Amy. Amy goes to Athens, John lives in Tulsa, and now the stream is exhausted, and the output is a map from city to string, yes. So what happens if there's a key collision? That's a very good question. Thank you. There are different overloads of the toMap factory method, and they give you back either a collector which will throw an exception if you get a collision between the keys, or alternatively, if you don't want an exception thrown, you can supply a merge function which will say what to do if there's a collision. Say, for example, I want a list created, and I want them put into a list. I want the values. In this case, it would be I want the values concatenated, something like that. Or the default. Well, no. Yes and no. So the question is, does the order matter? Well, if you're going to get an exception thrown in the case of a key collision, then the order doesn't matter. If you are going to say, for example, the decision was you wanted to concatenate these values, then the order would indeed matter. I didn't ever say, I think, that the order doesn't matter in which elements come down the stream. Yeah, the order does indeed matter. Yep, absolutely. Okay, so last of all, for these terminal operations, as I say, for these collectors, I'm going to look at classifiers because these are really important. Just one simple one. There are a variety of these, and they're very composable. So the classifier function takes elements, and the values that are placed in the map are lists of the elements, one list corresponding to each classification key. So for example, if you wanted to make a mapping from the city to the list of the people that live in it, you would use person.getCity, and that's the example that I've got here. So we're grouping by the city. City will be the key to the resulting map, and we'll get a list of the we'll get a list of the people that live in each city. So here comes Bill, and he goes to London, and Amy goes to Athens, and John goes to wherever John goes to. Or John goes to London this time. He's not in fact in Tulsa. And when the stream is exhausted, then what you get is that map. So you may be saying, I hope you're saying to yourself, wait a minute, what if I don't want a list there? Maybe I want something else. Well, the collector API will handle all of that. It's much more complicated than I have time to talk about here. But you can maybe see the essence of it. This is just really very powerful, and you can do a lot with it. One thing that is really important to emphasize about it is that you'll notice that the results, the containers that these values are being collected into, I've said there were things like array list and hash map. And you know that array list and hash map are not thread safe. And yet I have been saying that everything that works for sequential streams must also work for parallel streams and vice versa. So what I've implied is that the framework is handling concurrent access to those containers. We're going to see that it's going to handle concurrent access to these containers for you. So even though your containers are not thread safe, nonetheless, you can feed parallels, the result of parallel computations into them. What if you're, so thread safety is guaranteed by the framework even for non-thread safe containers. Obviously, there's an overhead here. You may choose to say, well, actually, I want to supply my own thread safe container. So if you do that, then each one of the methods like toMap and groupingBy, which result in maps, has a dual, which allows you to say, it's okay, you don't need to handle the thread safety, I'll do it, or rather my container will do it instead. Okay, so now I've talked about, I've gone around quite a long route to give you for sequential streams. I've given you the sources of the streams. I've talked about the operations, transformations on the streams, and I've talked about sinks as well. And I've given most emphasis to that because that's actually the most complicated and the most functional part of the API. I was going to talk about writing a collector, but actually I think I'm not going to do that because we're short of time, and also because I don't really want to give the impression, as I might do, that writing a collector is something that you have to do yourself very much. You would do it if you wanted to accumulate to a collector that doesn't implement collection, because all the platform library ones do. If you wanted to share state between values being collected, and also if you wanted to parallelize iterative-looking problems, which was actually the reason why I wanted to talk about it here, because I thought, well, it would be nice for you to know that we always, or almost always, can find solutions using this idiom to things that we just think have to be iterative. But I'm going to skip that. And maybe tomorrow I'll get a chance to look in on that. So actually, yeah, okay. So that will bring us back on time. So the one thing that I haven't really talked about so far, or the two things I guess I haven't talked about, the sync operations I've talked about do work for parallel streams, but I've only talked about iteration as a source for parallels, for streams. And of course, for parallel streams, iteration's no good. You don't want to only have a single element being fed in one at a time, because what you want to be able to do is to split your data down so that it can be worked on by streams in parallel. So this is where the splitterator comes in. This is where the split part of the splitterator comes in. Here I'm imagining I've got an array, or it could be a list, provided it was a random access list. This doesn't work at all well with linked lists, but if it's an array list, it would work very well. And the splitterator, the job of the splitterator is to split the data set down until it's got individual component data sets here, which correspond, and actually what it does is it actually looks at the number of hardware threads that your platform has and gets it to the right number for that, on the assumption that that one thread's going to be assigned to each one. And then at that point, we'll imagine here that what we've got is each one of these data sets is one for a thread to work on, and each thread can then iterate over the elements of of its data set and feed these simultaneously into the parallel streams. So we can now have a look at we can try and visualize stream operations now. This is my picture of them. We've got the splitterator on the left, intermediate operations. I've only got one of them there, but of course you'd have very many, and a reduction at the end. And this is roughly what it looks like. And obviously the big benefit of having parallel streams is the idea that you're going to be able to execute these intermediate operations in parallel. Tomorrow I'll talk about the performance aspect of that, when you can get some gain from that and when you can't, which is quite often. And I'm going to say very clearly that the advantages of using the functional style of the Stream API don't depend on you getting the performance gain that parallel streams give. It's nice if you get it, but you often won't. Nonetheless, streams are still the way to go. And then, of course, once the intermediate operations are over, then mutable, then the reduction occurs. You don't have any guarantee, even for sequential streams, you have no explicit guarantee that things will really happen the way I showed them there. So it may be that, for example, x0, the thread executing x0, or even if there is no thread executing x0, the processing x0, it's still entirely possible that even in a sequential stream, the implementation may choose to execute them out of order. So it executes, so it processes x0 and then x2, and then x3, and only then goes back to x1. So that's a possibility. And what you have to realize is that that has consequences for trying to observe a stream, for example. Supposing for instance, you have a peak operation in there, and you want to, you're wanting to look at to see what order the values you're going to print out, the values that as they pass through the stream. Then what you will see will be first of all x0, and then it'll be x2, and then it'll be x3, and so on. So it's important to realize that although in the end the Stream API will always preserve the correct order for if you have, for example, in this case, I'm imagining that we've got a data structure at the start for which ordering is important. It's not a hash map for which ordering isn't important. It's an array list for which ordering is important. Then the Stream API guarantees to preserve it. But it won't internally preserve it. So you have to be prepared to say that, to behave as though the streams were being executed in parallel. Okay, so if I can get this thing to move on. Right, next slide. Here we are. So now I come down to the question. Finally, what does parallel ready mean for your code and for the Stream API? What we have to get used to is the idea that sequential execution isn't the norm any longer, even though it's not an issue of performance. It's an issue of programming style. And it's an issue of future-proofing your code. Sequential execution is no longer the code. It's still often more efficient, but you don't know whether in the future there'll be more and more areas, more and more use cases where parallel execution will become more efficient. And so you should write your code as though that situation was already here. And you might think, well, hang on a second, that means I've got to go to a lot of trouble to make my code parallel ready. But actually, the benefits of making your code parallel ready even if it's not going to be executed in parallel, already outweigh the disadvantages. The disadvantage is you've got to learn stuff. The benefit is you get clearer and more maintainable code, more concise and more maintainable code anyway. So writing your code in a parallel-ready style is already a worthwhile thing to do. And that means your code must be agnostic about its execution mode. It's got to stick to the rules of the Stream API. And that means that you have to remember that operations in the Stream API have equivalent effect whether they're executed sequentially or in parallel. And if they're non-deterministic in parallel, like for each, for example, then in principle you have to regard it as non-deterministic sequentially as well. Even if by accident it often happens that they come out in the right order, that's got to be the rule. And this is useful because actually what this is going to do is it's going to decouple the idea of decoupling execution mode from functional behavior is like that to do with that mailing the letters example. What you're doing is you are actually removing from your mind a constraint that you've imposed unnecessarily, that ordering is important. So a lot of the time it's not, and you'll get better algorithms if you take that constraint away. And parallel ready is not only about parallel execution. So the question is your code parallel ready? Originally, that was what this talk was entitled. Is your code parallel ready? And the answer is, well, probably it isn't. I shouldn't think so, because some of the time you are going to have to think of new algorithms. Not often, because the Stream API provides you with an awful lot of already created classes for what you're going to need. All the collection handling is already there, ready for you. Sometimes you will have to think about it. You need to cooperate with it. That's actually really the main requirement. And it depends on you behaving sanely. Where sanely is as documented by the Stream API documentation. So the JavaDoc for java.util.stream actually tells you what I'm going to say now, but it's not very digestible, and I don't think they did a great PR job on it. You've got to avoid stateful behavioral parameters. So that means like the lambdas that we saw in the filter and map. The results can't depend on any state which might change during the execution of the stream pipeline. So you can't look at any external state and use that for a behavioral parameter. Oh, I know what that was. That was a kind of joke. Yeah, sanely or safely. Yeah. Non-interference is important. You can't modify a stream source during execution. You can't do that by any means at all, either from within the stream's operations or from outside. The assumption is that once a stream has started evaluating, the values in the source are going to remain the same. The only exception for that is for thread-safe collections like concurrent maps and so forth. Otherwise it's hands-off once stream evaluation has begun. Don't rely on side effects. So peak, for example, or for each and so on. Don't use that for accumulation. You really do have to think of functional style terminal operations if they're not already provided. And that's it, really. I don't think I missed any of the. I don't think I missed any of the requirements. No, I didn't. So the conclusion is the Stream API is great. It provides a functional style framework for programming bulk data operations. If you do it right, then you can get parallelism with nothing more than a single method call. You just put parallel you just call parallel from your stream, and it will automatically be executed in parallel. Tomorrow I'll talk about the occasions, the situations in which you want to do that, but you can do it at any time, and it should produce functionally exactly the same results. All we've got to do is cooperate with it. And hey, you have to end with a good slogan. So parallel ready code starts today. I'm afraid I've run over. I'm only within a minute of the end. I guess I've got time for one question. If anybody has one question. No? Okay. Well, thank you very much for listening. I do recommend you the book.